Okay, and then we have a quantifier, and this one is law 5. When you see this one, negate existential x. Okay, for x is equivalent, as you said, as for all x is negate p. Okay, same goes to if you negate for all x p is equivalent to existential x negate p. When negation is applied, when negation has been applied, okay, and then to quantify expression, it flip the quantifier as it move inward. Right? Okay, we have outside and inside. Applied quantified expression, it flip quantifier, it move inwards. And the negation turns all the universal quantifier to existential quantifiers and vice versa, lah, and negate all the predicates. Okay, this one is law number 5. Okay, for the universal quantifier, is for every or it equivalent. It called as a universal quantifier. Okay, consider we have a free and bound variable. Okay, we have bounded. Okay, when it close to the quantifier. Okay, we have n greater than 5, equation 1. Okay, and then we have okay, for some n is a natural number whereby n is greater than 5 is equivalent to lah. In equation 2, the variable n is bounded. Okay, it is a existentially quantified variable. And then in equation 1, n is free, uh, as its values may not be determined or restricted. Okay, why equation 2 are bounded? Because it is you have the quantifier in front. Okay, this one is free and bounded variable. Okay, for example, here we have people like stropine. Okay, for all y people, and then y like stropine, or x like Richard. In this segment, y and x are two variables. Okay, we have defined x and y, and whereby the y is universally quantified. Okay, y is quantified, and it is bound. Okay, y is bound because you can see y is quantified by universal quantifier. Okay. Okay, and then in this statement, we have for all x, okay, and x is a member of P. The occurrence of x in the declaration is binding. Any occurrence of x in a P are bound, and any occurrence of any variable other than x are free variable. Okay, free and bound variable. When you see the when it is free, because it is not bounded by quantifier. Is it okay? This one in a predicate logic, predicate logic, free and bound variable. Okay. Again, free variable in any formula, it occurs at least one in a formula without being introduced by one of the phrases. For example, we have for some x, for all x. Okay, a formula S in which X occurrences as a free variable will be called a condition. Okay, what is what is the difference between free and bounded variable? Okay, depend on the variable. Okay, if you have to swap out the variable for another, if it doesn't, then you have to you have a bound variable. Okay, and then if your function depend on your variable, then you have a free variable. Okay, and then we have a substitution. Substitution in logic. We have for some n, whereby n is natural number, and then n must be greater than 5. We may replace the name with any term of t, provided that t is the same type as n. It must be the same type. First requirement for substitution is the same type. And then the process called substitution that denoted by ptn. It denotes that the fact that the term is being substituted for the variable name in the predicate p. Okay, example, we may denote the substitution of 3 for n in the predicate n greater by 5 by replacing the 3 for the n. Okay, how to do that is n greater than 5, and then we substitute 3 for the n. Also, we may denote the substitution 3 plus 4 for n in 5 n greater than 5 by n greater than 5, and we want to substitute the 3 plus 4 for n. Okay, and please remember substitution is only for the free variable, it's not for the bounded variable, and not for the bounded variable. Okay, by substitution, you can also known by 3 plus 4 for n. Later, therefore, 3 plus 4 is greater than 5. Okay. Okay, more than one substitution. This one is nested substitution in case that is more than one free variable. Consider the predicate x is happy and y is sad. We have a conjunction here. Conjunction. Okay, and then here x and y are both free variable. We may substitute a niggle with the x as follows. X is happy and y is sad. And then we want to replace a niggle for x is equivalent to niggle is happy and y is sad. Okay, we replace the x here. Okay, and now you can substituting the can for y. Okay, we have a nickel is happy and y is sad, and then can you want to replace a y. Okay, and then therefore you can say that nickel is happy and can is sad. Okay, you want to substitute the the value for y. Okay, okay, so far do you have any question? The soalan ke? Okay, basically for the substitution is the fundamental concept in logic. Basically, when you talk about the formal logic, substitution is a syntactic transformation on formal expression. This one is formal expression. Okay, formal expression here. You want to replace the x. And then to apply a substitution to an expression mean consistently replace for each variable placeholder symbol by other expression. Okay. Okay. Similarly, in the one step overall substitution may be denoted as X is happy and Y is sad, and then you want to replace it overall substitution and not step by step as before. You can have two like this. X is happy, and you can do a nickel by replacing X, and can by replacing Y lah. These two substitution take place sequentially. First, as is nickel is substituted by X, okay, for X, and then can is substituted by Y lah. However, for simultaneously substitution like this, okay, X is happy and Y is sad. Okay, to illustrate the differences between sequential and simultaneously substitution, consider the following example. Okay, this one is the is equivalences for x greater than 3. Okay, and y uh, okay x greater than 7. You want to replace y for x and 8 for y. Okay, this one is you substitute simultaneously. Okay, this one is step by step. Or we call it as a sequential. In the former, there they one only one occurrences of y, and the later there are two occurrences of y. Okay, step by step, you need to replace occurrences step by step, one by one. Okay, fine for this one. Okay, do you have any question for the substitution? We change uh, the values. Okay, uh, okay, and then for substitution, again, it is not a notation. It's a notation whereby the notation must be free. It's not bounded by the quantifier, and it is a formula that obtained from the A or from the predicate, okay, or occurrences by substituting the term for every occurrences of y lah. Okay, if for example if you have e, okay, and then we have a t to replace by y. Here we can say it's a formula obtained from a by substituting the terms t for every y in every free occurrences of y in a. Okay, for this one. Again, for is a formula obtained from A by substituting the term T for Y in every free occurrences of Y in A. Okay. Okay, for example, we go by the example. Nak bagi kamu faham sikit. Okay, let's say we have A, okay, and then we want to substitute A. Okay, for example, we have Y, and then we have P O X. Okay, okay, and then we have for some Z. Okay, we have Z is a member of Y. Okay, for some uh, Z is a member of X. Okay, this one you replace it. And then we have okay, this one is you replace it. Replace the term step for every y in every three occurrences of a in occurrences of y in a lah. Okay, which some term are not allowed. For example, here, okay, here we have some z, and okay, we have zy implies for all x. Okay, this one is allowed. When you go by the a, when you want to replace x by y, this one is not allowed. Why? Why not allowed? Ani Syairah, tahu ke kenapa dia tak allowed? Ani Syairah, Afiq, Afiq Husaini, tahu ke why it is not allowed? Rufinus, tahu ke kenapa dia tak dibenarkan? Why? Okay, thank you. It is because it is bounded. Not allowed because the following is the bounded occurrences by the quantifier. And then we have a restriction. Restriction is some sort like filters. Filters that you want filters some of the rule in the predicate logic. Okay, for the restriction, you restrict you restrict some of the existential elimination. Sometimes it is we call it as existential elimination. One of the key limitation or restriction in a predicate when it is applied only on the atomic proposition. There is no way to talk about the properties that apply of category to the object or about the relationship between those properties. Okay, this one is a restriction. For example, considering the example all natural number n which are prime numbers and are greater than 2 are odd may be written as follows. Uh, for all n, whereby n is a natural number and n is a prime and n is must be greater than 2 implies n is odd. Okay, you filter. Okay, and then using filter by the statement, you can be write as follows. Okay, restricted the statement. Okay, or occurrences by using this symbol. Okay, here is the occurrences or the syntax. You have a quantifier quantification. Okay, you want to quantify the quantifier, and then you have the restriction. Okay, and then the predicate. Okay, and then the predicate. Okay, restriction n must be prime. This one, for example, n must be prime, and then it is what is a predicate to apply upon the filter. Okay, this one is another example. Restriction also can be used in existential quantifier because sometimes it called as the existential elimination. Sometimes it also is existential elimination. Okay, restriction can be also used in existential quantification. For example, there has been a female British Prime Minister, may be written as okay. For some P, okay, it's a people. You write the quantification or quantifier. Okay, whereby okay, you restrict the P must be female, and you explain the predicate. You explain the predicate. P was a prime minister, and then you have universal quantification, restriction, and then predicate. And then universal quantification restriction also implies the predicate. Okay. For example, we have for all n, whereby the n is a natural number, n is a prime, it's a restriction condition, and n must be greater than 2. And then the predicate, okay, n is odd. Same goes here, n is prime, okay, implies n is odd. These both two are similar, equivalent. Equivalent. Equal, Equal. Equivalence. Okay, represent the following statement in the form. Everyone who likes cheese like bread. There is a person who likes cheese that likes bread, and everyone who likes cheese also like bread and likes bananas. Okay, you can try to solve that one first. Okay, I give you 5 minutes. Okay, for this one, okay, we have everyone also like cheese, like bread. Everyone, you can say P is people, and then you restrict P like cheese, and then you explain the predicate P like bread, P like cheese, and P like bread. And then next one, every there is a person who like cheese that likes bread. Okay, is a people also. Okay, the restriction like cheese, also like bread. Okay, okay, this one is for some. And then everyone who likes cheese also like bread and like bananas. Okay, it's a P, people. Okay, and then you have restriction like cheese and okay, this one. And then for the predicate, you need to have a conjunction. Okay, conjunction. Okay, so far, do you have any question for the restriction? You restrict the okay, you restrict the uh, some quantification. And then sometimes you name it as existential elimination. Okay, do you have any question so far? Is it okay? Boleh ke? Okay, this one is uniqueness. Uniqueness quantifier allow us to represent the statement such that there is at least one X such that must be unique lah. Okay, uniqueness must be unique lah. In order to be more specific, consider there is exactly one such that. Okay, we have for some X whereby n, and then this one is the predicate X plus 1 equivalent to y. It is the case that the predicate X plus 1 is true for exact one natural number 0. Okay, if you have 0 and then it is true because if you replace the value 0 plus 1 equivalent to 1 okay. Okay, if you have 1 plus 1 equivalent to 2 is false okay. Okay, this one is the for the predicate okay. Okay, any question? Do you have any question so far? Okay, another uniqueness example okay. We have the uniqueness quantifier is not really needed as the restriction that there is a unique x such that px can be expressed as. Okay, you have another example. Okay, example number one. If if px okay denotes okay, let's say denotes okay or represent uh, x plus 1 is equivalent to 0 okay, and then and you declare u is integer okay, then you say for some x px okay, is true okay. Another example, but if px if p x denotes or represent x is greater than 0, then you say that for some, okay, x px is false. Okay, the unique quantifier is not really needed. Okay, as the restriction that is unique x size px can be expressed as, okay, you can express this one as, okay, you can denote this one such as some x, okay, and then px, okay, and for all y, okay, and then py, okay, implies y equivalent to x. Okay, next. Okay, the operator which allow us to state there is exactly one natural number x is denoted as follows lah. Okay, an example we have x1 x. Okay, sometime when you put the uniqueness, you can put either exclamation mark. For this one, you put the exclamation mark, and sometimes you put as a one. Okay. Okay. For example, here we have for some x n, and then the predicate x plus 1 equivalent to 1, and then you can say that for some okay, country, okay, and then the predicate c is rich lah, which is unique lah. Okay. Okay, assuming that the statement it is sometimes useful to pinpoint exactly which element of x holds for which predicate p holds. Also, it is convenient to perform a sum operation on its value lah. Okay, the mu operator is allow us to do exactly for this purpose. The statement of mu x x restrict p is read as the unique x from the set x such that p whole of x. Okay, for example, you have here mu x n restrict by the x plus 1 equivalent to 1, whereby the mu is associated with the value of 0. Okay, this one is same goes to the here. Okay. Okay, and then uniqueness also the element that type does not possess the relevant property, then we are free to construct a statement of given previously lah. Okay, on the other hand, the mu expression that are not associated with the unique element can generate an undefined value lah. For example, the mu expression un and you restrict the predicate, and then n is even and mu 3 country, and then the population C is must be greater than 10 million. Both undefined lah. Because uh, you associated with the mu operation. Okay, this one is undefined. Okay, because it not possess a certain type of property lah. And then it is for some reason it is free variable that can be constructed as the given statement. Okay, so that we can incorporate this one is the solution the term into set comprehension, that we can apply the term mu expression in the form. Okay, mu x where you restrict the p as a t, and then you must return the result of applying the term t to unique of the element of the set x, whereby satisfy the predicate p. It is capital start with the r, and then it gives the values of KSA. Okay, mu c country, and then you c is rich, and then you define the predicates. Define the predicates p. Okay, and then when you define the predicate p, it give the values. Okay, so far do you have any question? Ada soalan ke? Okay, if there is no unique element that possesses the relevant properties, then the result is undefined lah. This one is we discussed before. And then please do the exercise. We have the following in term of new expression: the tallest mountain in the world, the head of the tallest mountain, the older person in the world, the nationality of the older person in the world, and the smallest natural number. Okay, please do this exercise. Boleh ke? Okay. Okay, and then here is the answer. The mu m mountain, whereby the restriction is m is the tallest in the world. Okay, and then here mu m, whereby the m is mountain, m is the tallest in the world, and the predicate head in meter. Okay, and then the oldest person in the world, mu p people, you restrict. Okay, this one is the oldest person in the world. And then the nationality of older person in the world. Okay, you have P people, and then you restrict people is the oldest in the world, and then the predicate nationality P lah. Okay, this one you can define it is either true or false. And then the last one is the smallest natural number. Okay, you have un, whereby n is natural number, and you restrict for all m n, and then the predicate n is less than or equal m. Okay. Okay, I think that's all for chapter 4.